Our first presentation of the afternoon session is Tianyu Guan. She's an assistant professor in the Department of Mathematics and Statistics at York University. She has a PhD in statistics from Simon Fraser University, and her research interests include sport analytics, machine learning, functional data analysis, and non-parametric statistics. Her presentation today is soccer analytics using event data and tracking data.
Hello, everyone. So first, I want to thank Guanyu for inviting me for this event. And then I want to thank all the organizers for organizing this wonderful event. I really like it. So today, I'm going to talk about my research in soccer analytics using event and tracking data. So the event and tracking data that I use is from the Chinese Super League. I know it's not obviously not the top league in the world, but I have a special feeling about this league because I grew up in China, and I watch some games in Chinese Super League, and also when I was in my first year in the university, my hometown team won the championship in the Chinese Super League, and we were very excited. So in the first jersey day, I planned to wear a jersey from my hometown team, but I couldn't find it. So I didn't wear one, but I guarantee if the next event will happen sometime soon, I will definitely wear one. Yeah. So my research focused on the CSL event and tracking data. And actually, this is a good data set. Although the league is not good, but the data set is very good. So we had access to all the games in the 2019 season. So that gives us 240 games of event and tracking data. And this is considered enough data for us to do something, to find some insights in soccer. I will first introduce the event data and then briefly touch a little bit about tracking data and then talk about my projects. So event data consists of chronological records of well-defined events like passes, tackles, shots, and so on. And characteristics of each event are also recorded, like players involved, the locations on the pitch, and the time of the match, and so on. So for each match, we have over 2,000 events recorded. And that means for 240 games, we have 240 multiply 2,000, this many of events happen. And the events data focus more on the on-the-ball activities. And then we also have access to the player tracking data, which includes the coordinates of the ball and the 22 players on the pitch. And we have high-frequency data that is recorded every 1/10 of a second. So roughly for each match, we have over 1 million rows of data to use. And you can consider this is big data, right? But then I will talk in the second and third projects, this is not enough data for us to use. And for the player tracking data, it helps us to monitor the off-the-ball player movements. So there are many research problems that we can do based on these two data sets. We can have tactical analysis, player and team performance evaluation, and also match outcome prediction, and a lot more different topics. So the first project I'm going to talk about is should you park the bus? So we all know here parking the bus is kind of a strategy that some soccer teams may use. But then every now and then we see some leading teams will use this strategy, right? But then we ask the question whether this is a good strategy to use when a team is leading. So this expression, parking the bus, was invented by Marino and refers to a playing style that is extremely defensive and unattractive, and is usually used by a leading team trying to protect their lead. So here our objective here is to develop that when a team is leading, whether it is a good strategy to play defensively. And here, our research is based on the assumption that the convex hull area formed by the players on the team provides a proxy for the defensive style. So on the left, there is a clip of the game, And the home team is in blue, and the road team is in red. And we can see the convex area by the two teams has a huge difference. And the road team is actually defending. And we can see all the players kind of squeezed in a very small area. So they have a smaller convex area comparing to the attacking team, that is the home team. And on the right, we have shown the convex area for the game. And we can see there are some up and downs. So that represents the transition between offense and defense. And aside from the event and tracking data, we also use the betting odds as another source of data. And we build a simple logistic regression. And our binary response, y equals 1 when the shots is, the next shots will be taken by the trailing team and 0 otherwise. And the covariates we use include the time of the match, and the goal differentials of the leading team, and the pre-match betting odds, and also the average convex area over the 60 seconds prior to the shots. So overall, we have around 1,800 shots in our data set. So this is our results, and we can see clearly that for the convex area, it has a small p-value, means that it is statistical significant, and the coefficient is negative. So that means like when the leading team is playing more defensively, and then the trailing team is more likely to take the next shot. Actually, like there is a perfect example of the message that we are trying to deliver. That is from Euro 2020 final. I think many of you may have watched this game, and England had a very quick lead, 1-0 lead at the second minute. But after that, they play very defensively, so they have no ambition to attack. And then we all know the results, so they eventually lost in the penalties to Italy. The second research I want to share is the comparison of individual playing styles in soccer. And this is motivated by the question that can we identify players who are similar in style to a given player? As an example, how can we identify a pool of players who have stylistic characteristics that are similar to a top player that a team is very hard to get, for example, Messi or Mbappe? So the challenge for this is that the playing style is difficult to analyze in this envision sports, and due to the the fluence of these sports. And so we partially solve this problem by combining the event and tracking data to provide both the on the ball and off the ball patterns of players' style. In detail, we develop a 39-dimensional player variables that captures as complete as possible the variables that related to a player's playing style. And these variables can be divided based on whether this event happens on the offensive third, middle third, or defensive third. And we also divide these variables based on whether the team is in possession or the opponent team is in possession. Here is a list of all the variables we defined on the offensive third. We try to be as complete as possible. For example, we include the average player position when the ball is in the offensive third and the team in possession. And we also include some percentages, such as the percentage of time a player has the ball when the ball is in the offensive third and the team in possession. So here, all these variables are defined when a ball is in the offensive third. And we have similar variables defined in the middle third and in the defensive third. And based on the 39 variables we obtained, we're trying to capture the style of players. So what we do is that we first identify the player that we're interested in as player 0, and then we try to compare an additional player to player 0. So the statistical model we consider is that for each player and each match, we can build a vector that contains the 39 variables. So that means for each player, because in the CSL 2019 season, for each team, it has 30 rounds of games. So that means for each player, we have a maximum of 30 such variables for the player. And we then can assume that these variables follows a multivariate normal distribution for a specific player, which is identified by the μj and sigma j. So here the problem arises about there is not enough data, because like here, as I mentioned, we have 39 variables, but for each player, we have a maximum of 30 matches of data to use. So if we use conventional method to estimate the parameters, we are unable to do that. Even if we split a match into first half and second half, sometimes we still have enough data, because some players may not attend a game, or some of the variables may be missing for the player. So it's still a very hard task. All right, so we will touch this a little bit later. But now for each player, we build a multivariate normal distribution. And then the next step is that how can we compare the differences of the players' playing style based on these distributions rather than a single metric. So now we want to use a metric called the KL divergence to measure the discrepancies about the players' playing style. And this is the formula. And the key thing here is that we need to estimate all the mean vectors and variance covariance matrices so that we can calculate this KL divergence. Like I mentioned, for the conventional method, it's going to be really hard to obtain relatively accurate estimators for the parameters. So we propose a hierarchical model and use a Bayesian framework to solve the problem. So the basic idea is that we assume that these covariances matrices came from the underlying distribution, and we will set some prior distributions for mu and the sigma. And then we can use the MCMC method to draw some posterior samples and use the posterior mean to estimate these parameters. And here we got an example using our CSL data. We identify the player 0 as Falani from Shandong Luneng Taishan, because this is a relatively famous player we can identify in the CSL. And Falani is a former Belgium international, and he is famous for playing for the Manchester United of the English Premier League from 2013 to 2019. And then we have 28 midfielders as the potential replacement for Falani. And here we calculate the KL divergence, and we can see the Polino from Guangzhou Ever Taobao is the most similar player to Falani. And you may have no idea about this because you don't know these players, right? So, to prove that our method makes sense, is reasonable, we consider that we can compare Falani himself to himself. So basically, the next step is to do a reliability check. So basically, we split Falani's own match into two parts, and then we compare the second part of Falani to the first part of Falani. So the results is shown below. As we can see, like the second part of Falani is most similar to the first part of Falani. So we think that our method is kind of reasonable. All right, so the last project is about a player's performance. It is acceleration and age. So this is a project that I personally like the most because like this is the quickest article that we finished and published in the journal. So it's very smooth. So this project is motivated by predicting future players' performance. Like this thing is kind of important for teams roster building. And also, like, if we want to evaluate a player's performance, we know that age is one of the most important factors regarding to performance. And young players kind of improve by age and then reach a plateau and then decline. So this is the rough pattern that we expect to obtain using our data. And the challenge here is that what is performance, right? So we have different metrics, but how can we identify what is performance? So we did literature review, and for different papers, they identify different metrics to use, but we don't know which one can capture players' performance most accurately. So here, we think that if we cannot find a uniform metric, And then how about to use something that we are certain of and easy to obtain from our data to kind of represent it? So we consider, okay, we can use maximum players' acceleration to kind of infer the performance of players, because we know with the tracking data, the maximum acceleration will be very easy to obtain. So like the ideal case is that for each player, we can observe the maximum accelerations over his or her entire career, right? But the thing is that our data is only focusing on one season. So that means we can obtain the maximum acceleration for players within only 1 year of their career. So this is the problem that we need to solve during our study. Our solution is that because I study functional data analysis, and then I did some literature review, and I consider, okay, we have powerful tools for that, because like in functional data analysis, if a functional data observed on only a short segment of the entire domain, we call them the functional snippets, and they are studied by some other researchers. So there are methodologies that we can use to build our analysis. And here is an example. On the left, we have the maximum acceleration for one player during the season of 2019. As you can see, we have on the x-axis, the age is within 1 year of span, right? And then that segment is only contribute a little piece on the right, where we play the maximum accelerations for all the players. So that means, as you can see, we cannot obtain the whole curve spanning over the entire age domain. We can only observe a small segment of that. So I'll talk about the formulas later, but this is the outcome we obtain. And this is our estimator, the average maximum acceleration versus age curve. And as we can see, this is exactly what we expect, right? When players are young, they tend to improve and then reach some plateau and then decline. So this is exactly the pattern that we want. So I will touch a little bit about the formulas. So we can use the tracking data to calculate the velocity, and based on the velocity, obtain the acceleration at any time point tj. And then we will scan over the players' accelerations during the entire match and find the maximum acceleration during that match. And then we can plot the curve on the left. And then we will use a local linear smoothing estimator to estimate the mean curve. And here, like in this loss function, we have a kernel and also a weight. So at the end, we also have a comparison of our average maximum acceleration curve with some other aging curves provided in another paper. And we can see, although the y-axis on the two y scales are different, however, the resemblance in the shape is amazing, right? So they all reach the plateau almost at the same time. So this tells us that if we cannot define what exactly is performance, but at least we can look at their maximum acceleration average curve to have some insights to help us build an idea of when the player reaches plateau and when decline. Yeah, that's everything. Thank you.